So welcome to engineersgetblue.com, and we have this problem in differential calculus which states that two points are moving horizontally in space at different heights above the earth. Show that the angle of elevation of the line joining them is greatest when the distance between them is least. So this is a maxima minima problem or optimization problem in differential calculus. So let's start to analyze first what is the situation here. So there are 2 points which are moving horizontally. That means if these 2 points are in space with different heights, then they are moving in parallel to the ground or to the surface of the earth. So if this is the surface of the earth, then the 2 points are here in space, so they have different heights. So the first point has height 1, which is h1, and the second point has height 2, h2. So in this case, the 2 points have different heights, but if the 2 points are moving horizontally, therefore their heights or their individual heights are constant. So in the second sentence, we have to show that the angle of elevation of the line joining them is greatest. So if we're going to connect the line joining the 2 points and extend it to the ground or to the surface of the earth, this will form an angle. This is the angle of elevation. So the angle of elevation theta is also a variable, which is if we're going to connect the two lines between the 2 points, this is also theta. So from here, we have to assign a variable for the distance between the 2 points, let's say s. And this distance, or this horizontal distance, vertical distance between the 2 points is h2 minus h1 from here. So I think we already have all the variables and the constants in this figure. So what we have to do is to form a working equation by using this s and theta as the variables and h2 and h1 as the constants. So if this is our theta, or the angle of elevation, we can use this side of the triangle and s. So the trigonometric function that we're going to use is sine. So sine theta based on this triangle formed, this is equal to the opposite h2 minus h1 over the hypotenuse s. So since we have to minimize the distance s so that we will achieve theta as the maximum, so we have to express s in terms of theta from here. So from here we have to cross this. S is equal to h2 minus h1 over sine theta, or this is equal to h2 minus h1 cosecant theta. So we have here the working equation s, or the distance between the 2 points, equal to the difference of heights h2 minus h1 times the cosecant of the angle of elevation theta. So from here, since this is our working equation and we have already expressed the other side of the equation in theta, or in the angle of this trigonometric function, so we can now differentiate s. With respect to theta. So as we differentiate, we have to treat h2 minus h1 as a constant. So we have ds over d theta equal to, we have to copy the constant h2 minus h1. Then the derivative of cosecant theta, the derivative of the cosecant theta is negative cosecant theta cotangent theta. So this is our derivative of s with respect to theta. Since this is a maximization minimization problem, we have to minimize s, therefore we have to equate ds over dt to 0. So from here we equate this to 0, so we are left with 0 equal to h2 minus h1 negative cosecant theta cotangent theta. So from here, if we're going to divide both sides by h2 minus h1, the h2 minus h1 will just cancel. This will just become 1. So let's continue. We have 0 equal to negative cosecant theta cotangent theta. So we're left with this equation. From here we have two quantities, negative cosecant, or we can multiply the both sides of the equation by negative 1. So this will become 0 equal to cosecant theta cotangent theta. So from here we know that there are two factors here. So we have cosecant theta equal to 0, cotangent theta equal to 0. So from these two values of theta, we have still to evaluate which is not part of the solution set in this problem. So first, let's consider cosecant theta equal to 0. So if we're going to simplify that, cosecant theta is 1 over sine theta equal to 0. So if we're going to cross this, simplify this in terms of sine theta, we have sine theta equal to 1 over 0. So if we're going to find what is theta here, or what is sine theta that will yield an undefined equal to undefined, so we have to find out what is theta that will yield an undefined of sine. So as we can remember in our trigonometry, sine theta, the function sine theta is continuous all throughout the values of theta. Therefore, there is no such value of theta that will make this sine theta infinite. Thus, it is also evident in its graph that sine theta is a graph starting from 0 and has values all throughout the values of theta. So, in this case, there's no such value of theta that will yield sine theta equal to infinity. Thus, this solution is not part of the solution set for this problem. So let's try this second. We have cotangent theta equal to 0. So from here, we have to simplify. This is 1 over tangent theta equal to 0. Or tangent theta is equal to 1 over 0 or infinite. So if we can remember in tangent in graphing trigonometric function tangent theta, there is such value of theta in the x-axis that will have undefined or has an asymptote line. So from that, we know that theta is 90 degrees. So if theta is equal to 90 degrees, tangent of 90 degrees will yield an undefined or infinity. So we know that theta is equal to 90 degrees based on this. We can also relate tangent theta equal to infinity because tangent theta is just the slope of the line. So if you can still remember in the analytic geometry, the one with the slope, the slope of the vertical line, which is 90 degrees, is undefined or infinity. The slope with 0 degree has a slope of 0, or the vertical or the horizontal line has 0, 0 slope. So this is m equal to 0, this is m equal to infinity. Thus, we know that theta is equal to 90 degrees. So this is now part of the solution set. Now we know that theta is 90 degrees based on this. So if we're going to consider back in our figure, if this point 1 moves faster horizontally to just beneath or under, directly below the point 2, if we're going to connect this line to the ground, this will become our angle of elevation 90 degrees. Thus, this will form the maximum angle of elevation in that case. So if theta is 90 degrees as the angle of elevation, or the maximum angle of elevation of the two lines, the 2 points connecting this line, we have to find out what is this minimum distance between the 2 points. But based on this graph, if point 1 is just directly below if point 1 is directly below point 2, this will become the least distance between the 2 points. Thus, in our solution, if we're going to substitute this maximum angle of elevation back in our working equation, we should arrive at h2 minus h1 as the least distance. So let's try to substitute 90 degrees. Try to substitute 90 degrees. So S equal to, from the working equation, h2 minus h1 cosecant theta. So at theta equal to 90 degrees, S is equal to h2 minus h1. So let's simplify cosecant. 1 over sine, and theta is 90 degrees. We know that sine 90 degrees is 1. Thus, we are left with this distance between 2 points as the difference of the heights of 2 points. So from here we have already a proof that if we have this maximum angle of elevation, if we connect a line joining the 2 points, we have 90 degrees as its maximum angle. If we have that maximum angle, we also have the least distance between the 2 points, which is in this case the difference between the vertical distance. So h2 minus h1, or the difference between the two heights of the 2 points, is the least distance if we have this maximum angle of 90 degrees. So that's all. Thank you very much.